Hey everyone, in this video we will understand how we can implement the binary searching algorithm using the recursion. In the previous video, I have already discussed what is binary search and how it works with the help of example. And we have also seen how we can implement this using the iteration. Okay, so if you have not watched that video, you can find the link of that video in the video description below. So in this video, I'm assuming that you know what is binary search and how it actually works. Okay, so keeping that in mind, I will actually start implementing the binary search using the recursion. Okay, and if you want to understand recursion from the basics, then you can watch my full playlist of the recursion, that is mastering the recursion. You can find the link of that playlist in the video description below. So now let's start implementing the binary search using the recursion. So basically in binary search, you will be given an array and you have to search a key element, right? Whether that is present in the array or not. Okay, so basically how binary search algo works, that we have seen in the previous video. We saw in the previous video this thing that we actually find the midpoint again and again between the low and high range. Okay, and we check with the mid element whether my key element is equal to this. If not, then I have to decide whether I should move to the left side or the right side of this mid element. Okay, based on whether my element is greater than this mid element, okay, or lesser than, I will move to the left or the right side. Okay, so basically I was searching for the 82, so I said okay, my midpoint will be 8, okay, for 0 and 17. Okay, then I checked with 45, it was not equal to 82, so I said okay, now I will move to which side? This side, because 82 is greater than 45, so 82 can be only this side. Okay, so I shifted my low pointer, to the 9. Then I again find the midpoint of 9 and 10, and it was 13, so I shifted to 13, right? And then I checked with 65, 82 is not equal to 65, so I said 82 can only be on this side, so I again shifted my low pointer, right? So low came at 14, and then I find the midpoint was 15. Then I checked, okay, my 82 is equal to this 82, right? That is midpoint. So I said okay, my key is present. Okay, so and we have saw other example also in which high pointer can also change, right? So this was that example. If you want to search for 55, if you apply the binary search, you saw that your high pointer was also changing from 17 to 12, okay, at one point of time, right? So your low and high pointer, they keep on changing, right? And if your element, let's say 53, you want to search and it is not present in this array, right? So your answer will come as key is not present. And this will happen when your low will become greater than your high, right? Low will cross the high, then your key is not present. So this is the condition for not present of any element. And we find the time complexity also. So time complexity, we got order of log n, and the space complexity, we got order of 1, that is constant space. Okay, now let's see the recursive solution. So basically to understand the recursive solution, I have taken here the iterative code. Okay, so it will be easier to understand the recursive solution using this. Okay, so basically what we have to do while we are writing the recursive code, okay, of any of the, you can say, problem, we have to see two things: how I can write the base condition and how I can write the recursive call or recursive function. Okay, so basically in this code here, we were actually changing the low and high, okay, in each of the iteration of the while loop, right? Now in this recursive solution, what we will do, we will call the binary search by changing the low and high. Okay, one time I will change the low and I will call this binary search, and in the another recursive call I will change the high and I will actually call this binary search. Okay, and in each of the recursive call, when I will come inside, okay, I will do some of the tasks, like I will check whether my element is present with the key or not. Okay, and basically I then make the recursive call based on whether I should change the low or high depending on where can I find the key element, okay, on the right side or on the left side. Okay, so basically as I'm saying that in every recursive call I will actually change the low and the high pointer, right? So here there should be actually two variables, low and high, right? So that we have the array, we have the key, and we have the low and high. So basically from the main function, I will actually initially pass low value as 0 and high value as n minus 1. For this code, n is 18, so your n minus 1 will be 17, and fourth parameter will be key. Similarly, here we have to change this. So now I have received low value as 0 and high value as 17, right? And now what I will do, again I will find the midpoint. Okay, So basically I am finding the midpoint. Midpoint is low plus high by 2. Okay, and I have already explained that finding the midpoint using this formula can lead to overflow in some of the situation. So you can watch that video, that how this low plus high can lead to overflow and what is the solution for this thing. Okay, so the solution of this is we can do some another thing that I will tell you later in this video. Okay, but for the explanation, do check out that video. You can find the link in the video description below. Okay, and that is a great interview question also, that why this formula can lead to overflow, okay, at some point of time. Okay, but for example, let's find the midpoint by using this formula. I find the midpoint and then I will check again this thing. So if your key is equal to A of mid, I will return true. Okay, and if it is not equal, then again I will check where should I move then. Okay, whether to the left side of this mid element or to the right side. Now if key is greater than, okay, so that means I will move to the this side of the mid element. Okay, so that means I should ask binary search A. Okay, and then now I have to change the value of low. So here low should be changed. So in the iterative code, I was saying low will be changed to mid plus 1. Okay, let's say mid is, let's say 8. So I was saying low will come to the 9. Okay, so here low will change to mid plus 1, right? And high value will remain same. Okay, that is, let's say if we are coming for the first time, low is 0, high is 17. Okay, so mid will become 8. So now here this will be 9 and high will remain as 17. Okay, and then key. Similarly, we can write this thing also. Here we have to change what? We do not have to change low, but we have to change high. And high is actually mid minus 1. That is, we are moving in this direction. Okay, so high pointer should be decremented. Okay, and last will be key. Okay, so this is the simple binary search recursive call. This is the recursive call and this is the recursive call. Okay, and what is the base condition or the stopping condition? The stopping condition is, one thing is whether we have found the element. Okay, if we have found the element, we will actually return. Okay, so this can also stop our binary search recursive code. Okay, and what if our element is not present? Then what will happen? Okay, then actually if we write this code and we want to search an element which is not present, then this can go into the infinite recursion actually. Okay, so how I will stop? Basically the element will not be found in the array when we will reach to a condition when low is greater than high. So basically before doing everything, I will just write that condition. I will just say if low is greater than high, return false. Okay, do not do these things, do not find the midpoint then. Okay, so yeah, this is the simple recursive solution or the recursive code. Okay, so this is the algo that we have just discussed. Okay, that I have written here clearly. Okay, so basically how this will work, let's take a simple example to understand it. Okay, more clearly. So basically I have taken a stack so that I can place the recursive function calls. Okay, let's say I want to search 55. Okay, so main will call this with low equal to 0 and high as 17. So now I have placed this function call on the stack. Okay, now I will check whether low is greater than high. No, so I will just find the midpoint. Okay, and this is the formula that we can safely use for finding the midpoint, and this will not lead to overflow. Okay, so explanation can be found in that video that I have just told you. You can find the link in the video description below. Okay, so now after finding the midpoint, I will check my key element with that. Okay, my key element will not be equal to this mid element. Okay, so I will just change. Okay, so I will just say, okay, if key is greater than A of mid, yes, 55 is greater than this 45. So I will check on this side. Okay, so I am calling binary search A of mid plus 1. Okay, so basically I have called binary search with 9, 17. Okay, so this is 8 plus 1, 9, 9, 17. Next function call will be for 9 and 17. Okay, and now here again I will check this. This is false. Again I find the midpoint. Mid of 9 and 17 will come as actually 13. Okay, you can just check by this. And after that, A of mid is equal key. I will say 13 element is the midpoint. 55 is not equal to this. So I will see, okay, where should I move? Okay, so my 55 is actually greater than A of mid. 55 is actually not greater than A of mid. So I will now search using this call. Okay, or I will do this recursive call. Okay, let's say this is the call number X and this is call number Y. Okay, so that I can recognize. So basically this was the call X. Okay, but now I will do this call. Okay, that is the call number Y. So binary search A comma, now what will be the value of the low? Low will remain as 9. Okay, but this high should change. Now high will come here. Okay, so that I can check only this thing. So high will come as this. Okay, so now again I will go here and this will become, I will become 12, right? So 9 and 12, I will check in between, I will find the midpoint, I will check in between. The mid will come as 10, and a of 10 is 55, 55 is equal to 55, so that means true. So from this, okay, I will actually return here. So basically I went from this point, okay, and I came to this point, I say return true. So basically in the same way I will move backward, I will move from here to here. That means this function call, okay, this function call is present in which function? In this function where we have the 9 and 17. We call this with 9 and 17. Inside 9 and 17 we called with 9 and 12, right? So we have come here. So basically we have come here. So basically you can think that this x is actually something like here, and this is the function call, this is like this function call, okay, 9 and 17. Okay, now what will happen? This will return again what? This will return true also. Why? Because actually here we have the return thing, okay, we have the return statement also. Okay, sorry, I forgot to write. Okay, here we have return binary search, return this binary search. So whatever true has come here, I will return to this, okay, and then whatever true will come here, it will be gone to main function, because every time whatever true is coming, we are sending return return. Okay, so return true, return true. So in the main function true will come and we'll say yes, my element is present. Okay, so same way you can check for the element which is not present. Okay, basically you will keep on doing that thing, and at some particular point of time low and high value come as such, so that low will become greater than high, then I will say return false. Okay, so every time false will come either to this or either to this, okay, it will actually return this false only. Okay, so false will propagate from up to down, that is to the main function also. Okay, so now let's find the time complexity of this recursive code. So basically to find the time complexity of the recursive code, we have the simple formula, that is we have to find the number of recursive call that are being done in the algo into what is the time taken in each of the call, or you can say cost of each call. Okay, so basically this step is very much important to find that how many number of recursive call or steps have been taken in running this algo. Okay, so basically the time complexity of the binary search is log of n. In iterative solution in the previous video we have seen. Okay, in the recursive solution also we will get order of log n only, but the way of calculation of this complexity will differ in the iterative solutions and in the recursive code. Okay, so let's see how we will do. So basically let's say x number of recursive call are being made, okay, in this binary search. Okay, it takes x binary search calls, so our answer will be x into, let's say cost is y, so x into y will be the time complexity. So we have to find the time complexity in terms of our input. Our input was, you can say n is the array size. As the array size grows, then what will be the order of the time complexity, right? So we have to find the time complexity in terms of n, and same for the space complexity. So basically how we can find the number of recursive call or number of steps taken using this recursive code. Basically here you can see if I want to search for the element which is not present, let's say 53. Okay, so maximum number of call will be taken when a particular element is not present. Basically for finding the 53, these are the recursive call, and this I have actually, you can say, explained in the previous video of the iterative solution also, and in the recursive code also. If you apply this you can see. Okay, so basically initially I will pass 0 as the low and high as the 17, then low will be changing to 9, then I will make a recursive call with 9 and 12, low as 9 and high will be changed to 12. Then I will make a recursive call to a99, that is I will come to here, low and high will come here. Okay, then I will find the midpoint will be 9, okay, again, and I will check whether my element 53 is equal to this 52. I will say no, so I will do this thing. Okay, and actually I will change the high, that is I will make this call, and I will actually do this call in which I will actually change the low mid plus 1, this. Now low has become greater than this. Okay, so in this call, when this will be 10 9, they will cross, I will say return false, so false will be returned to each call. Okay, and finally main function will get the false. Okay, so how many maximum call we have like taken in this? 1 2 3 4 5. So basically in binary search, what we were doing, if we have the array of size n, then we were finding the midpoint, okay? And let's say if we were finding the new midpoint, okay? New midpoint was coming, let's say 13, and then we were saying, okay, let's say I have to leave this part of the element. That is, now I will check only these elements. So let's say from 9 to 17, we have 8 elements. I have to check only these elements. That is, you can say nearly 4 elements, 9, 10, 11, 12. So I have to check only half of the this n by 2 element, right? So in this way, at some point of time, the element will become 1. Only one element I have to search, right? And in how many steps I will get to this particular position that I will be remaining with only one element. So basically in the first step, I was getting half of the element in which I have to search, okay? And in the second step, I got only n by 4 element in which I have to search, right? In the third step, I will get only n by 8 element, okay? My search space will reduce to n by 2 to the power 3, right? 8 can be written as this. So in the kth step, okay, what will be the number of element that I have to search? This will be n by 2 to the power k, okay? So for this example, let's say k is equal to 3, then we have to check only n by 2 to the power 3 element, that is n to the power n upon 2 to the power k. Now at some point of time, when this n by 2k will become equal to a, that means this, okay, then I will stop my binary search, okay? So using this formula, I will actually find the value of the k, okay? So if I solve this, this is this, and if I take log base 2n, okay, log of this, okay, so this will give us simple k, and k will become log base 2n, right? So that means these are how many steps, okay, till the point from n to 1. This will be like first step, then in the second step my element will be reduced to n by 4. In third step my element will be reduced to n by 8. Element means the search space, and let's say in the log n space my total element will be reduced to, or you can say search space will be reduced to only single element, and my then binary search algo can stop. So my total recursive call will be log of 2n, okay? In each of the, you can say, steps, it is doing this thing only, okay? It is reducing the range, okay? So in log 2n space, in log 2n steps, okay, so it is taking log 2n recursive call. And in each of the recursive call, what we are doing, we are checking this thing, and this comparison will take just order of 1 time, because this is a simple constant time operation. Next we are finding the midpoint, which again can be found in O of 1 time. Again we are comparing this O of 1 time. Again we are comparing this or either this, okay? And depending on then we are making the call. So again this operation can also be done in order of 1 time. So basically you can say constant time is being taken in each of the recursive call. So cost of each call is like order of 1, okay? Simply you can say order of 1. The total number of recursive call is like log of 2n into order of 1 is the cost. So this will be log 2n. So your time complexity is basically, you can say order of, okay, big O of log 2n. So in the worst case, your total number of call will be log of 2n, okay? This is the worst case, okay? And in the best case, what can be the time complexity for this? So basically the best case of this algo is again order of log 2n only. Why? Because if your element is present here also, then also it will find the midpoint, and it will first check here, right? Then it will come to something like here, okay? Then only it can come after some number of steps here, okay? So it will basically take log of 2n, okay? So best case for this binary search will be log of 2n only, okay? Now what is the space complexity of this code? So basically space complexity will be decided by stack. That is how many maximum number of calls are being placed on the stack. So in the worst case, actually how many maximum number of function call will be placed? So basically it will depend on the number of recursive calls, right? So basically in this binary search, as we have seen earlier, that number of recursive call that are being made are log of 2n, right? So log of 2n number of recursive call will be placed on the stack, okay? So as these calls are being placed on the stack, so all these calls will take the space. Your space complexity will be equal to log of 2n, order of log 2n, right? So this is due to the stack space, okay? The space that is being taken by stack in recursion, okay? In iterative solution, we saw that there was, you can say, constant amount of space was taken in the, you can say, stack, okay? Only one call will be placed on the stack, okay? Because there was simple for or while loop, okay? So constant amount of space complexity will be there in the iterative solution. Okay. Now before ending this video, there are some important points. So basically, we can also write the time complexity as theta of log n, because the exact number of log n calls are being placed or are being done, okay, while we are implementing or while we are executing this binary search. Okay, so to show that log 2n is actually the exact time complexity, so that's why we can use the theta. Okay, so this will be like, you can say, the tight bound answer, okay, for finding the time complexity or to tell the time complexity of the binary search. Okay, and in the same way as exactly log 2n number of calls are being placed on this text, so space complexity can be theta of log n. Okay, so this is the, you can say, best answer. Okay, although this big O of log n is also okay, but this will be treated as the good answer. Okay, theta of log n. And the method that I have shown to you for telling the time complexity, it was actually similar to the recursion tree method. Okay, that is one of the method to find the time complexity, or you can say to solve the recurrence relation. Now what is the recurrence relation? So actually I explained what is recursion and how we can solve this recurrence relation in the video of the design and analysis of algorithm. So you can check out the videos under that playlist. Okay, you can find the link in the video description. So basically recurrence relation is a simple mathematical equation, okay, that can actually show or depict the any recursive code, okay, in a mathematical form. Okay, so basically if I want to write this binary search algorithm in a mathematical way using a recurrence relation, then I can write in this way. Okay, so basically t of n is the time taken to solve the problem of size n, and here actually in this binary search, what we were doing, we were dividing our problem of n size again and again in half, right? Again and again, if we have the input n, then we were dividing it into half size. Okay, if we have the input as n by 2, okay, we have the size of the array as n by 2, then we are again doing it half, that is we were actually only solving the n by 4 part. Okay, so in each of the step we were actually doing the half of the given input. Okay, so this is actually the way in which we are dividing our big problem into the sub problem by dividing it into half, okay, in binary search. And in each of the recursive call we were doing some constant operation like this. Okay, these are the, you can say, constant operation that we have seen. Okay, so basically this is treated as cost. Okay, so basically this is the recurrence relation for the binary search. Okay, and keep in mind that we will not place 2 here. Okay, 2 into t of n by 2, we will not write 2 here. Okay, because we are only solving only half of the problem in binary search. Okay, we were actually neglecting half of the part of the problem, and then we were solving only the half of the part in each of the iteration. Okay, so basically there are various methods to solve the recurrence relation. They are, so basically there are various methods to solve this recurrence relation. Some of our recurrence tree method, master method, and substitution method. So basically this method that so actually the method that I have shown to you, okay, to find the time complexity, it was basically based on the recursion tree method. Okay, some call as recursion tree method or some call as recurrence tree method. Okay, now the solution of this recurrence relation is basically t of n equal to theta of log n, which we can find using any of the method. Okay, basically this solution is actually the telling me the time complexity. Okay, the solution will give me time complexity. Okay, for space complexity you can just use the method to see the number of recursion calls on the stack. Okay, so you can watch my dark playlist in which I have shown that how you can solve this recurrence relation. Okay, and you can find this answer. I provided the link of the recursive code of the binary search in the video description below, so you can check out the link there. It is for all for this video. In the next video, we will see other questions based on the recursion. If you have any question, please write down in the comment box, and do like, share, and subscribe the channel. Press the bell icon for further notification of the video. See you in the next video. Till then, goodbye.